Alright, so we just finished solving problem 2. What I want to do next is in class I said, as a challenge in terms of preparation of the exam, try and update your code so that you solve our CSTR design problem for a range of tile values and look at the computed conversion and selectivity, or if you couldn't, if you don't want to work with conversion or selectivity, look at the concentrations as a function of tau, right? And so we can think about, what would be the tau that might optimize the performance of my reactor. And so what I'm going to do is I'm going to come back over and actually it's CSTR solver. So I have my code here, and this is the video we just finished. And so I have this top function with no inputs. It passes CA naught to it because we needed CA naught in the top function to compute conversion. But then essentially it solves my CSTR design problem and then returns back the conversion and the selectivity. Right. Cool. And then this was my solution down here. CA naughts commented out because I pass it from above. And yeah, and so tau is defined here. And so what I want to do, and tau is V divided by V flow, right? So it's 2 initially. Okay, so what I want to do is I'm going to start by just running, right? I'm going to make sure this is giving me the right answer. So we hit sol as CSTR solve, and I get this. Okay. First thing I want to do is I'm going to come down to my bottom function. And where is tau? I'm going to comment out this material here. V and V flow are just used to compute tau. All right, and so tau is this. So instead I'm going to make tau an input. Okay. And then here I'm just going to say tau. And so I'll say tau is equal to 2. And then I can add tau as an input here. Okay, so I commented out tau within my error function, instead made it an input, okay, defined tau in my top function, and then just added it to these variables I'm passing via this anonymous function. And now if I run it, I get the same exact answer. Great, so everything seems to be running. Alright, so now what I'm going to do is if I'm going to look at a range of tau values, is let me maybe create a vector of taus, and let me then loop over those values of tau and compute the conversion and selectivity. Okay. And so what I'm going to do, okay, is sure, tau is 2. Okay, what I'm going to do though is let me create a vector of tau values. Okay, and so what do I want to do for that? I'm going to say tau is equal to, let me use linspace. Now I don't think I quite want to go down to 0, because if I go to 0, they're not going to have any reaction, so CD and CU will both be 0. I'll have a conversion of 100%, but it might cause issues with my selectivity. So let me instead just make it some small number maybe. Let's just do say 0.1, and then let me go up to say 100 minutes. And yeah, we can use the default length of 100. That's fine. Okay. All right. So then what am I going to do? Well, let me loop over my tau vector. Okay. And what am I going to do each loop iteration? Well, I'm going to solve. Right. So I'm going to put this material that I have for solving. Only when I solve, I'm going to point to the ith element of my tau vector. Okay, I will solve. Okay, and then let me kind of look at this animal. Okay, so what do I need to track? I don't need, well, before we had CA, CD, and CU, and then we computed my conversion, right? So let me do this. Let me say compute conversion. So my conversion, before we had this, Okay, and actually I'm gonna create a vector to store my conversion. So vector of tau values, let me create a vector to store conversion and selectivity. So my conversion of A, I'll do zeros, and I'll do size of, make it the same size as tau. And then my conversion, or my selectivity of my desired relative to my undesired, well, that'll be the same zeros and same size as tau. And so tau is a row vector. Conversion and selectivity will both be row vectors. Okay, so if I compute my conversion, okay, I could say my conversion of A is equal to, so looking at what I had before here, okay, it's going to be CA naught minus CA. Okay, well, that's going to be the first element of this SOL vector here for my output, divided by CA naught. And another way I could do is I could just store all of my concentrations to vectors, and then I could just use vector operations to compute it afterwards. Actually, let me do that. Let me do vector store conversion and selectivity. So let me do vector to store concentration of each species. Okay, and then we'll just compute what I want afterwards. So I'll have a CA, CB. And that way, if I wanted them all, I can get them. This way I have everything, and so I can get it if I want. And so then I'm just going to say store my concentrations, and so CAI is going to be equal to sol1, CBI is going to be equal to sol2, CDI is going to be equal to sol3, CUI is equal to sol4. Okay. And then what I'm actually going to do initially, so let me delete this. Okay, I'm going to comment this out. Is what I'm going to do to make sure this is running correctly is I'm going to open up a figure window, figure 1. And we can do hold on, and I'm going to plot tau versus CA. I'll plot tau versus CB. I'll plot tau versus CU or CD. I'm going to plot tau versus CU. And I'm going to have I'll just add a legend. And so my legend will be CA. Yeah, CA, CB. And actually, I just do A, B, D, and U. This. X label will be tau, and that's in minutes. My Y label will be C, and that's going to be in moles per gallon. Okay, so let me just do this. So I'm not returning anything. I get a plot. All right, I have an error. I spelled legend wrong. Okay, so let me try again. Bam. All right, now I just get an error that I'm not actually returning any variables at this point. Okay, but now I have a nice plot. So here's my concentration of A being consumed, my concentration of B being consumed. Here's my concentration of D, which goes through a maximum. And then here's my concentration of my undesired component, right, which steadily ramps up and increases. Okay, so cool. That's a pretty cool plot. And so I have that. Now, if I wanted to compute the conversion, okay, I could do that. So let me do compute conversion and plot. And actually, I can get it set up so that I return my conversion. So let me just say, let me define it separately. So my conversion of A, okay, is going to be CA naught. Okay, now I have the CA vector. I'll do element-wise operations, divide by CA naught. And then let me just I'll return this for now. Okay, but then let me plot. And actually, let me open up, say I'll call this figure 2. And so in figure 2, I'll plot tau versus my conversion of A. My X label's the same. My Y label, though, now will be conversion of A. Okay, so if I run this now, okay, now I have figure 1. Now figure 2, here's my conversion of A versus tau. So I can get a sense of where my conversion begins to approach 100%. Okay, and it gets returned since I didn't suppress anything when I called it. And now if I want selectivity, okay, so now if I want my selectivity, so my selectivity, my desired relative to my undesired, it's going to be CD period divided by CU. I'll put this in figure 3. And so now I'll plot tau versus my selectivity. X label's the same. My Y label, though, now is my selectivity, and I'll say CD divided by CU. Okay, so if I were to run this, okay, now I have figure 1, figure 2, my conversion, and then here's my selectivity of D relative to U. Alright, so it looks like as time increases, my selectivity actually decreases. Okay, cool. So now I have 3 plots for each cases. Alright, if I wanted to return this, okay, maybe I actually return 2 optional variables, selectivity of my conversion of A and selectivity of D and U I could return. So I don't need to call this res. Okay, and this is looking pretty cool. Okay, I can delete this now since I have that. In terms of lens space, I could add more to it. Right, I could try going to a slightly smaller value of 0. Okay, I run this, I get some result. All right, the other thing that I'm going to compute that might be useful is we could update our settings so it's suppressing the output every time. Okay, but it might be nice to be able to check to make sure that our function was converging correctly. And so what I might do is I can collect, remember, these flag variables to check to make sure that convergence was successful. And I've got to leave here in a couple minutes. We've got this. So let me just do zeros. Size tau again. Okay, and what I'm going to do is when I solve, you know, and I just as well could use vector or matrix to store everything, but this is fine. Whoa, now I got to try and remember. So if I if I type help fsolve, I believe it's the third argument's the flag. Just, yeah, so one. All right, so we're looking for positive flags, and it is, yeah, exit flag's the third argument. So I don't want the second, and then the third, I'll write to the ith element of this flag vector I'm creating. Okay, cool. Because then I can make it so I can return flag, right? And I could even just add a check within my function that, if, right? And so we can return it, but you could also add something like if flag I is, say, greater than 0, then I can display, I don't know, so display the value of I, and then I'll display, check solution. Okay, but you could also then return that vector as well. Oh, so now if I solve, well, I guess I'm better off returning it. Why? Because I was just displaying a value, right? You could throw an error in there, maybe even, but let me, so let me return conversion, selectivity, and then let me get my flag. So now I solve it. I have all my figures. Okay, here's my flag variable. All right, if I just open up this way and look, all right, they're all ones, all right, which is great. That means it's solved and there was no issue. I said after the exam, we'll discuss modifying the options with fsolve. So we don't, one will be we can make it so we suppress the output like this. But then we can play around with adjusting the tolerance and all of that stuff. But I hope that's good practice as you prepare for exam 1. I've got to run to meeting, but if you have any questions, just let me know.